Welcome to PCB Chat, where we talk with experts across the printed circuit design, manufacturing, and supply chain fields. I'm Mike Buetow, president of the Printed Circuit Engineering Association. I'm joined today by Andy Shaughnessy, our new content architect at PCEA. Andy and I worked together years ago on Printed Circuit Design magazine, and it is great to have him back with us.
Glad to be back.
And our guest today is Scott Bright. Scott is co-founder and COO of Cadstrom, a new company that is coming up with tools for resolving some of the engineering problems that designers and engineers are running into right now. If you recognize the name, it might be because Scott has been a serial visionary and entrepreneur in the engineering industry for years, including 3 years at IoT company Jiva, where he was CEO, and 13 at the engineering firm Synapse, which he co-founded and was CEO. Hi, Scott, and welcome to PCB Chat.
Hi, Mike. Hi, Andy. Thanks very much for having me. I appreciate it.
Scott, you've been around the printed circuit industry for years, and I know you've attended PCB West in the past, but is Cadstrom your first pure-play ECAD company?
Yes, it is. I've spent my career in hardware product development and never really imagined I'd be building a software company. But the opportunity and the timing was right, and the need is very, very great. I'm sure we'll get into that.
Okay, well, let's talk a little bit first about what it is that you're doing and what the problem is that you're trying to solve.
Sure. So, as I mentioned, I've kind of been in this space. I've had the good fortune to be part of or lead some pretty world-class engineering teams. Designed hardware from back-of-the-envelope sketch to high-volume manufacturing, literally hundreds of times, everything from NASA to Disney. And in 35 years of developing electronics products, I'm fairly certain I have never gotten a design, at least a complicated design, 100% right on the first try. And to those outside the industry, that sounds a bit like a horrible admission, but for electrical engineers, they all kind of nod and, yeah, that's how it goes. You take your best shot at a design. Inevitably, you miss something critical, and the cost of that is immense. Time, money, headaches, and many of those faults that show up late are actually preventable. The thing is, these aren't exotic edge cases. Engineers are good at what they do, and they get the hard stuff right more often than not. These are fundamental validation issues that today's tooling doesn't solve. And Cadstrom is a pretty neat way to take a load off the plate and give engineers time back.
And now a word from our sponsor. Join the electronics design and manufacturing industry at PCB East 2026, coming April 28th to May 1st to the DCU Center in Worcester, Massachusetts. Sponsored by the Printed Circuit Engineering Association, PCB East features more than 120 hours of expert electronics design, manufacturing, and assembly training. The annual one-day exhibition will be held April 29th and features major semiconductor companies such as AMD, Altera, Lattice Semiconductor, Microchip, and Samtec, along with leading software developers and manufacturers. Registration for the conference and exhibition is now open. Be sure to book your spot. For more information about PCB East, visit pcbeast.com.
So, Andy, I know that you and I have talked to many, many founders over the course of the last 20, 25 years. And it seems like a lot of them start with a problem that they're experiencing themselves, right? Mm-hmm. Before they say, right. Look around, can't find a solution to it. I guess I need to create my own.
Right. And it's interesting that you seem to be focused most on the schematic area where there hasn't been. I mean, it's kind of like the Wild West. You don't see a lot of companies focusing on that, and people just still do stuff on napkins or whatever. So, was there some failure at that level that led you to focus there?
It's a great question, Andy. If you stop and think about it from an outsider's perspective, when you're drawing a schematic in today's advanced CAE tool, generally that tool has no knowledge of the parts that you're putting down. It's a pretty picture. You're connecting lines between components on pins. Fundamentally, how is that much different than a drafting table and a pencil? But all of that information is available. Manufacturers go to excruciating lengths to provide detailed data sheets. But all of that information is really hard to access. It's unstructured data. And it requires engineers to keep it all in their head as they're designing. And that's the fundamental flaw. So, yes, there's greenfield opportunity everywhere you look here. But I love your term, the Wild West, because that's where the biggest pain is. It's also kind of the hardest problem to solve.
Mm-hmm.
My co-founder, who came up with the origins of the idea behind Cadstrom, was very frustrated by this problem. But she comes from a software background.
Mm-hmm.
And she kept thinking to herself, there has to be a better way. Because she works in an environment where you have this robust CI/CD pipeline that checks every time you make a change, does unit testing, tells you, advises you that you've done something to the code that's going to cause a failure. Why doesn't something like that exist for hardware designers?
Mm-hmm.
And she set about conducting research and building prototypes and spent the better part of 6 years as a passion project working on this problem. And eventually came to a pretty incredible working demonstration of an expert system that could solve many of these problems by looking deep into the components and how they're interconnected and examining that network. The problem was it was going to require engineers to manually put in an enormous amount of information about every design before it could do its job, which is an absolute non-starter. Nobody has the time to do that.
Mm-hmm.
Right about this time, she was on the verge of literally tossing this whole thing out, and the first commercial version of ChatGPT came out. And it was an epiphany. This is the data transformer that was necessary to structure that unstructured information and provide it to the expert system. That was the birth of Cadstrom.
And Scott, you spent the last couple years working on some, I guess, developing some expertise on the AI side of things.
We were very fortunate to come under the wing of the Allen Institute for Artificial Intelligence, the AI2 incubator program. And I had the privilege of spending a year with truly world-class experts in this field. And so it gave us the confidence that we were on the cusp of being ready to crack this problem. But the interesting thing here is that it's this hybrid of a deterministic expert system with the stochastic data transformer that LLMs provide. And that hybrid is really, I think, the power for solving problems like this in the real world.
Got it. So it's not just a pure LLM, where I could have just solved this problem by using ChatGPT or Claude or something like that.
I don't know if you ever tried to ask advice about a design from any of the foundation models. They're very good at telling you, you are absolutely correct. That is great, or that is a problem. Now ask them to explain why, or ask them the same question 3 times in a row and get different answers every time. Yeah, it's not right. It's not the right tool.
Well, context is critical, right? I mean, we all work under constraints. And one of the things that I noted when I was looking at the Cadstrom website is here on the PCB design side, we always talk about design rule checks. We're looking back at, did we do everything the way that the manufacturer wants it? What I see on Cadstrom, it's ERC, not DRC. So can we talk about that?
Sure. I think ERC and DRC have some things in common. Number one, at least in my experience, is they're very good at giving you a sea of red flags, most of which you can probably safely ignore. Unless you spend an inordinate amount of time configuring the checks for specific things that you're looking for. And even then, they're kind of peanut buttered across the design. As a quick example, you might have a rule of thumb, which is basically what ERC or DRC is, that says bypass capacitors should be very close to the components they're bypassing. Well, what does close mean? Turns out, if you take the time to build a SPICE model, you can simulate this, and you can get a deterministic answer about how close is close enough based on current and frequency and equivalent series resistance and everything that goes into that calculation. But who has the time to do that for every single bypass capacitor on your design? This is an awesome place for automation to take over.
But I'm just curious, in a situation like that, how do you train AI to make these sort of judgment calls that the double E's have to do? Where, it's like we'll say shall or should or, all these sort of things. I mean, it's like you almost have to train the AI to know, to be able to really just judgment calls, which I mean, isn't we like to think that AI isn't quite able to do that yet, but I guess are we at that point now where they are making a judgment call like that?
Well, I think your question is a very common one. And the answer is a little abrupt, but we don't train AI. We don't need to. We don't really use it for that kind of a question and answer. ChatGPT is a generalized pre-trained transformer. And essentially, that is the underlying thing that LLMs are very, very good at. They transform data, stochastically looking at a combination of sequences of letters and what's the most likely reply to that sequence. And they do that by having a vast ability to stochastically structure. We come at it from the other side. There are classes of problems that we know happen often. Does this problem exist in this design is actually not an ambiguous question. You can hunt for the clues that tell you that that is a problem or is not a problem. But you first need to have access to all the underlying data that gives you that analysis. So it's kind of a reverse way of looking at things.
Scott, why don't you walk us through how an engineer would actually use your platform?
Sure. So Cadstrom is essentially an automated platform that handles many of the fundamental design validation checks that engineers know need to happen. But frankly, they're tedious, they're time consuming to do manually, and they're prone to missing things, particularly when you're under time pressure. That's how the head and hand mistakes consistently still slip through the cracks. They cause huge headaches. So our goal is to free up design engineers to focus on high-value architecture decisions and creative problem solving, rather than spending lots of wasted time manually checking whether your 1.8 volt part will reliably talk to your 5 volt part, or verifying that capacitors have sufficient derating margins, or that you've properly assigned the interface resource on a particular flavor of a micro given the pin count and packaging, or I could go on and on, right? These have all certainly happened to me. They're embarrassing, but they still happen. And they happen to competent engineers every day. And frankly, it's not their fault. It's not my fault. We're under incredible time pressure. Inevitably, it's that footnote in small text on page 212 or some other hidden errata sheet or app note that will confirm the issue, but only after it's discovered the hard way. So what we're doing is introducing a new part of the flow. On the fly, we automatically build proprietary simulatable models for every component in each design. And then we provide a clear, detailed report back with the anomalies, which includes data sheet citations, supporting evidence. This allows engineers to fix the mistake and resubmit for checking again. And here's the interesting thing, the opportunity here from an automation standpoint. We believe strongly that catching errors early as part of the design process is crucial. It's crucial to accelerate design cycles, and kind of for the first time ever, we can now give engineers a way to reliably find problems way before the design is finished and ready for the traditional review. So you don't need to have everything fully specified. You can take the design file set, whether that's in Altium, KiCad, or CAD, ask Cadstrom to do an analysis on that design file set, and we provide this detailed analysis back. This is something that can happen independent of the engineer's other efforts, so it frees them up to start doing other things with their time.
So I'm stuck on that word proprietary, okay, and here's why. There are millions of components available. So if I'm working off of a particular, say, a TI part or a Micron part, right? How would that differ? You've built your model for that part. Would OEM designer A, B, and C all see the exact same thing, or is it really specific to each OEM or user of your platform?
The models that we build are dynamically built on the fly during design ingestion. So there isn't like a setup or a configuration or a pre-training necessary here. And that's important for a few reasons. One, I don't know how many versions of STM32 there are available, but it's a lot. And two, they go through revisions. There's errata, there's new updates, there's app notes. So we don't ever assume that we know everything about a component. We may have already analyzed something very similar to that. We may have already built a model that we can base on. But the first thing we do is verify if there's anything different in this particular version of this part in this design. And if so, we amend the model for the rest of the analysis.
You mentioned OrCAD, you mentioned Altium, you mentioned KiCad, I think. Does the Cadstrom tool, does it integrate with that, or is it on top of it? So you'll take the data from one of those tools, run it through your ERC.
So we're not a plugin, we're not integrated, we're an adjunct, we're an accessory, and we handle the design by ingesting the raw design file set. So there's no translation step. You don't need to export a bill of materials, a net list. We take care of all of that. But more so, where this is going, once you have this report that shows you what the problem is and all of the supporting evidence that allows you to believe that it is a problem, and also a pretty big clue on how to fix the problem, the next logical step is you want to start to interrogate your design. You want to be able to ask questions. Well, what if I twiddle this knob? What if I adjust these parameters? What if I swap out this part? And that, I think, is the power of having this tool built into something that is outside of your normal CAE tool, because CAD tools aren't built for that today. This is something kind of new. It's, you're asking the question, am I achieving my design intent? And how can I validate that? That is a piece that's been missing from CAE tools.
Is it to the point where you can actually ask those questions using real language? That was supposed to be one of the values, right, of the LLMs, is that, you don't necessarily need to be an engineer or a coder to be able to extract the answers that you're looking for.
Well, I'm super excited about this, but I don't want to overpromise. Not yet today. Today, we're really focused on finding the problem, showing it to the engineer, and giving them a heads up that they can quickly spend 30 seconds or a minute solving that problem before it costs them months and tens of thousands of dollars and huge headaches downstream. The next step in Cadstrom, the next evolution, is to actually give engineers access to the tooling that they can start to ask these questions, and a natural language interface would be a great way to do that.
I imagine the KiCad supporters are really happy about this just because it's open source, and I'm sure they have ideas of building all this functionality in, right? What's their response been, I wonder?
Well, I think there's an interesting opportunity here to remain agnostic to any individual tool chain, right? We want to try to support engineers across the spectrum. And so we've built the tool, we've built the ability to handle and ingest raw design files from all of these tools. That was a fairly heavy lift, to be truthful. But it's in service of our primary mission, which is giving engineers time back, kind of for the first time ever. Instead of asking them to do more with less, faster, now we're taking a load off their shoulders. And we surveyed hundreds of engineers in the process of figuring out where to start. And out of that series of interviews, we developed a stack ranked list of the problems that commonly happen. And we started tackling that list from the top down. We're still working our way through it. There's still more to go. We don't solve everything, but we do have a guaranteed list of things that we will find. And it's pretty amazing when you tell an engineer, hey, I analyzed the design and I found this problem and here it is. And they're like, oh yeah, that's a problem. That would have bit me. That would have been embarrassing. Thank you very much. I'm going to fix that. Let's run it again. Okay, it's fixed. No new problems are induced. Let's build a board. We have, over the last year, about a little over 90% of the designs that we analyzed had some showstopper problem that the engineering team did not know about beforehand. And a large number of those would have been very expensive respins. Design partners over the last year have reported a 10x ROI on implementing this as a fundamental accelerator to their validation process over the year.
What's the number? I forget what the percent is, but something like 70% of manufacturing problems could be fixed or eliminated in the design process, and the left shift and all that. The earlier in the design process, the better. But I mean, it's something like 70% or more, I believe.
Yeah, it's the equivalent of not checking your source code before the compiler starts to run.
Well, whoever does that.
And, it's easy to underestimate the costs of respins too. I mean, an average modest complexity design is going to see 3 to 5 spins, and those are in the neighborhood of $30,000 in 6 weeks each.
And it's just built in too.
It's just built into the schedule. Everybody assumes this is the way it's always been. This is the way it's always going to be. Right. It's a rule of physics, but it's not.
I remember when Nick Brathwaite was the CTO of Flextronics, and he was telling me about a particular large server project I think they were doing. And he said it had something like, you had the motherboard and 16 daughter cards, and it went through 20 respins. And so each one of those boards had to be respun at about $50,000 a piece. I mean, so you're talking $20 million or more just in prototypes. So yeah, you're right. It's enormous cost.
Say nothing of the opportunity cost of all the engineers that spent their time doing that, trying to prevent it, then fixing it.
Yep.
What could they have done with that time? Taken on new projects, done more. This is one of the reasons I'm super excited about this. I think that, we're on to something pretty important. There's a lot of buzz today about using AI in all kinds of fields. It's not hard to find. You can toss a stone and find somebody trying to generate designs with AI. Mm-hmm. In my humble opinion, they are amplifying the validation problem. If an AI designs a circuit for you, how do you know it's right?
Right. There are whole rules, schools of thought about, how that it is possible. There are a lot of people saying that, you just have to have the right prompt and, sure. And eventually that AI will design a board, on its own. And there's a lot of people that in our industry that believe that,
Well, I think at some point in the future, I would not be surprised to see that happen for a certain class of problem. But there's a fundamental corpus of knowledge to train on problem here that isn't going to be solved anytime soon. And you still have the question in your mind, is the only way to validate this to build it and empirically test it? So I do feel like it's a pretty bright future for across the board. It's kind of a cool time to be an engineer, frankly. We're being given superpowers and we're just trying to figure out how to use them right now.
Well, trust but verify, right?
Yes, well said.
Let's talk about your distribution channels. So is Cadstrom available right now? And if so, how would somebody access it?
Today, we are on the cusp of launching this as a SaaS platform. We're still a little ways off from that. What we're doing today is operating in the interim as a service review bureau. So customers today zip up their design files, drop it into a secure repository, hit go. And they can go about their business and come back when the report's finished. Typically on a modest complexity design, it takes a matter of 24, 48 hours, a little longer for more complex designs. That's going to change in the near future, where the back-end tools that we are using to run this automated platform will be in the hands of customers and they can start running it themselves. But we're still a little ways away from that.
What are you doing about the IP security?
Oh, that's a question that has never not come up.
Sorry to be redundant.
No, it's one I usually have to lead with. There's a couple of things that I think are worth pointing out. Cadstrom never allows customer IP to be trained on by an AI. We exclusively hand the publicly available datasheet information to LLMs for data extraction. And the IP is kept in a secure environment. We are SOC 2 compliant, and we take data security and integrity very, very seriously. We're built from the ground up to assure that just like any highly secure cloud platform, these are the crown jewels for our design partners. We have to respect and make sure that we're keeping that very closely tight.
Do you see any potential use for this towards the back end, maybe? Traditional DFM tool area, towards data handoff? I mean, it seems seems like there might be some application there. But of course,
the sky is the limit here.
Yeah.
I can envision a future in which you're prepping for agency approval. And what is that but just another set of validation criteria that you need to pass? A complex, accurate enough digital twin could assure you are going to pass FCC, FDA. That's a pretty neat idea. Instead of having to redesign for manufacturability, what's the process you're going to be building for? Let's do that from day one. I think there's a pretty cool, interesting future where automated analysis has its fingers in a lot of downstream back end things. But we got to start with the front end. That's where the problems originate.
Seems like you and Margot sort of complement one another. Saw her interview where she said, now this is the year of physical AI, or physical AI is back. And how do you all work together in this?
Yeah, it's an exciting time to be an engineer. It's kind of an even more exciting time to be a hardware engineer. Over the last decade, software ate the world. I kind of feel like right now, hardware's biting back. Physical AI needs a body to run on. And if that body has faults, everything comes to a grinding halt. So the teams that will win here are the teams that figure out how to get to valid hardware faster. Margot and I do complement on each other quite well. She is, and I say this, quite realistically, I'm not exaggerating. She's one of the smartest people I've ever met. She's also extremely persistent. She does not take status quo and accept it as inevitable. She found this problem and said, there has to be a better way. I've spent my life assuming that there was no better way. And so a lot of the underpinnings that we've built on are her brainchild. That said, we also have a healthy tension. We see the world a little differently. I have a deep background in building hardware. She has a deep background in building software. How you go about building software, I've come to understand over the last few years, is very different. And so it's been a great education on both sides.
You're right about that, right? The hierarchy of it is completely different.
The hierarchy, the pace, the process. I'm used to water flow, critical path, Gantt chart, deterministic outcome, measurable progress, earned value analysis. Sprints with you're never finished, you're always improved. This whole fundamentally they're very different things.
Right. It's like the IC guys look at the PCB guys and go, why are you doing it this way?
Yeah, that's another question that I've heard a lot, and I think there's a really interesting opportunity to apply some of the same methodologies in semiconductor design.
Mhm.
It's fundamentally different. You have a smaller number of building blocks. They're put together
Mhm.
in much more complete ways, and the process of designing an IC is very, very different. It starts with behavioral descriptions and synthesis, and what's happened in semiconductor design is that they grew up with tools that provided a baseline ability that weren't there previously. Frankly, CAD tools for electrical engineering haven't really had to innovate since the 1990s.
Mhm.
Scott, for those who are interested in learning more, where would they find out?
Go to cadstrom.io, click a link, schedule a meeting. I will talk to you directly in person.
No AI.
No AI
No
necessary.
chatbot.
Yeah.
Scott, do you have anything else you want to share about Cadstrom and what you're working on before we wrap?
As I mentioned, it's a pretty amazing time to be an engineer. Whether you're coming at this from PCB fab or on the front end of design, we are being handed superpowers. We're still figuring out what that means and how to employ them. I think in any time of great change, there's reason for anxiety being part of that change. But I think there's also kind of a reason for enormous optimism. Um, the fun parts of my job as a design engineer, I can focus more on those because I now have things that take the rote drudgery off my plate. And I think that is where this industry is going and kind of needs to go.
Well, Scott, we certainly appreciate you joining us here in the new year on PCB Chat. For Andy Shaughnessy, this is Mike Buetow. Have a good day.